Tesla's next Gigapress is being described as the machine that deletes welding robots from the factory floor, casting huge sections of a vehicle in one shot, instead of stitching hundreds of parts together. That sounds like the next manufacturing earthquake, but there is a problem. The confirmed public machines are still measured at 6,000 tons and 9,000 tons of clamping force, not the 50,000-ton monster spreading through viral posts. So the mystery is not whether Tesla changed manufacturing. It did. The real question is what changed in 2026, what stayed exaggerated, and which breakthrough matters more than the myth. The biggest 2026 factory rumor is not the giant press. It is the claim that Tesla removed half of its welding robots because one new casting machine made them obsolete. That version is too simple, and the location is wrong. The real Fremont story was about a product change. Tesla ended Model S and Model X production there, then repurposed that floor space for Gen 3 Optimus production. That matters because a line built for humanoid robots does not need the same body shop layout as a car line. Removing or relocating welding equipment in that building would not prove that a new vehicle process deleted robots. It would prove that the factory stopped building those vehicles in that area. Cybercab belongs to a different story. Tesla has tied that vehicle to Giga, Texas, and the unboxed manufacturing system, not Fremont. In the unboxed approach, large modules can be built in parallel and joined later, instead of moving a full vehicle body through a long traditional sequence. That changes where labor, automation, and joining equipment are used. So if someone shows Fremont changes and says, "This is Cybercab production," the timeline does not line up. Fremont's conversion points toward Optimus, Cybercab points toward Texas. Mixing the two creates the illusion that one mysterious machine arrived and erased a huge section of the factory overnight. The real breakthrough is more specific. Tesla has been reducing the number of parts, welds, fixtures, and handling steps needed to assemble a vehicle structure. Castings helped start that shift, but they are only one part of it. If welding robots were not simply deleted, the better question is this: what actually reduced the need for traditional welding? The answer starts with Idra, an Italian machine builder that had spent decades making high-pressure, die-casting equipment for the automotive industry. Tesla wanted something more extreme than a normal aluminum casting cell. It wanted to turn a large section of the vehicle body into one shot of molten metal, squeezed into a die with enormous force. That was not a normal supplier request. Traditional body shops were built around stamped steel parts. Panels and structural pieces were pressed, positioned in fixtures and joined by welding robots. The process worked, but it created long chains of parts, measurements, clamps, weld points, inspections, and correction loops. Tesla pushed Idra toward a much larger machine, and the first verified breakthrough showed up on the Model Y. The rear underbody, which had previously been assembled from around 70 separate pieces, could be replaced by one large casting. That single change removed a whole section of part handling from the factory. The impact was not just that 70 became one. Every removed part also meant fewer edges to align, fewer fixtures to hold them, fewer welds to make, and fewer places where tiny dimensional errors could stack up. In a welded structure, one small variation can force the next station to compensate. In a casting, the geometry comes out of the die already tied together. That is why Giga casting changed the body shop. It moved some of the work upstream into the casting process, before the body reached the welding line. Instead of asking robots to join dozens of components into a rear structure, Tesla could install a large finished section and build around it. There were potential vehicle benefits too. A continuous casting can improve stiffness because the load paths are not interrupted by as many joints. It can also simplify crash structure design because engineers control more of the shape as one piece rather than stitching many smaller pieces together. But this was never magic, and it was never as simple as pressing one button and deleting a factory. Giga casting replaced a messy welding problem with a different industrial problem: molten aluminum, massive dies, cooling rates, porosity, repair limits, and machines so large that the factory has to be designed around them. Inside the casting cell, the process starts before the press ever moves. Aluminum alloy is melted in large furnaces at temperatures high enough to keep it fully liquid, then held within a controlled range so it flows correctly without damaging the metal quality. If the melt is too cold, it may not fill the die. If it is too hot, it can increase die wear and create other problems downstream. The molten aluminum is also cleaned before injection. It can pass through filtration systems that catch solid impurities, while degassing removes dissolved hydrogen that would otherwise form bubbles inside the casting. Operators and sensors watch for contamination because one oxide film or trapped pocket of gas can become a weak point in a structural part. At the press, the die is not just an empty mold waiting for metal. It has to be heated, sprayed with release agent, and checked, so the casting will separate cleanly after solidification. The release agent also helps manage temperature on the die surface because cooling has to be fast enough for production, but controlled enough to avoid distortion and defects. Then the two halves of the die close under enormous clamping force. This force matters because molten aluminum is about to be injected at high speed and high pressure. If the die opens even slightly during the shot, the result is flash, scrap, or damage to the tool. Vacuum systems help pull air out of the cavity before and during filling, reducing the chance that gas gets trapped as the metal rushes through thin passages and thick structural sections. The injection itself is violent and precise. A measured amount of molten aluminum is pushed into the die, fills the complex shape, and begins freezing almost immediately against cooled steel surfaces. Internal cooling channels carry heat away from the die, helping the part solidify quickly enough for a production rhythm. A real cycle is not a fantasy where one machine spits out multiple car bodies every few seconds. For a large automotive casting, the cycle is commonly discussed in the range of around 80 to 90 seconds, or roughly 1 to 2 minutes depending on the part, alloy, cooling strategy, and handling system. After the die opens, robots remove the casting, trim excess metal, and send the part for inspection. The impressive part is not just that a huge component comes out in one piece. It is that the machine repeats this sequence over and over while controlling heat, pressure, vacuum, timing, and metal cleanliness tightly enough for structural use. And that leads to the obvious question: if this process is so powerful, why can Tesla not simply scale it to 50,000 tons overnight? A 50,000-ton Gigapress sounds like the next logical step, only if clamping force is treated like horsepower on a spec sheet. In real manufacturing, that number is not a confirmed Tesla machine, not a verified production program, and not a known target for the next vehicle platform. It is better understood as a dramatic way to describe the dream of casting even larger sections of a car. The largest confirmed Tesla-related Gigapress is the 9,000-ton machine used for Cybertruck parts. For Model Y, Tesla uses presses around 6,000 tons. Those are already among the most extreme die casting systems ever applied to mass-market automotive structures, and they required new tooling, new alloys, new quality checks, and new factory choreography. Scaling from 9,000 tons to 50,000 tons is not a casual upgrade. A larger die becomes harder to build. Heat, cool, align, and service. Molten aluminum has to flow across longer paths without freezing too early, trapping gas, tearing, or creating weak zones. Thick and thin sections cool at different rates, which can cause distortion or internal stress. The press itself would also reshape the factory around it. Bigger clamping force means larger foundations, heavier platens, more powerful hydraulics, more complex extraction systems, and much higher maintenance demands. If a die that large fails, the downtime is not a small repair problem. It can become a production bottleneck measured in lost vehicle output. Cost matters too. A casting only makes sense if it reduces parts, labor, tooling, and assembly time enough to justify the risk. At some point, making the press bigger can create new problems faster than it removes old ones. The real story is not that Tesla has secretly deleted welding robots, with a mythical 50,000-ton monster. The real story is that casting has already changed the boundary between body design and factory design. The next generation is less about one gigantic press and more about a new manufacturing architecture built around fewer parts, shorter lines, and faster assembly. The manufacturing headline behind Cybercab is not a bigger casting machine. It is Tesla's unboxed assembly method, because that changes the order in which the car is built. A traditional auto factory treats the vehicle like one object moving through a long sequence. The body is assembled, then painted, then fitted with wiring, interior parts, glass, seats, battery, suspension, and final trim. Each station depends on the station before it. If one step slows down, the delay travels down the line. Unboxed assembly breaks that pattern. Instead of pushing one unfinished car through a single path, Tesla wants to build major sections separately at the same time. The front structure, rear structure, battery pack, interior module, and side assemblies can each move through their own work areas. When those modules are ready, they are brought together near the end. That sounds simple, but it changes the factory layout. Workers and robots no longer need to crowd around a nearly complete vehicle in a narrow sequence. More tasks can happen in open access positions before the car becomes a closed shell. Seats, wiring, electronics and trim can be installed when the module is easier to reach, rather than after the body has already limited access. Giga castings fit into this system because they reduce the number of pieces that need to be managed. A large front or rear casting can replace dozens of stamped parts, brackets, and welds. But the casting is only one ingredient. The bigger breakthrough is designing the vehicle and factory so those simplified sections can be prepared in parallel. This is why the Cybercab matters even before production numbers are known. A two-seat robo-taxi with fewer variants, fewer options, and no driver controls is an ideal test case for a different build flow. There are fewer combinations to manage, and the vehicle can be designed around assembly from the beginning. If Unboxed works at scale, the payoff is not just fewer welding robots. It could mean less floor space, shorter production time, different labor requirements, and a factory where the final line is no longer the center of everything. So, what happens to the robots? The short answer is, many of the classic body shop welding robots lose their job, but the factory does not become less automated. In a traditional body shop, robots spend a huge amount of time positioning stamped steel panels and joining them with spot welds. If a rear underbody is made from dozens of separate pieces, each piece needs fixtures, clamps, handling, and weld points. Replace that section with one large casting, and a whole chain of welding stations can disappear with it. It does not mean Tesla stops using robots. It means one category of robot becomes less central because the product no longer needs as many welded joints in the first place. The automation shifts upstream and downstream. Castings still need to be removed from the press, cooled, trimmed, machined, measured, and inspected. Robots or automated systems still move heavy parts between stations. Vision systems still check dimensions. Machines still cut mounting surfaces, drill holes, and verify critical points before the casting can become part of the vehicle. Then, the joining problem changes. Instead of thousands of spot welds across stamped panels, Tesla may rely more on structural adhesives, fasteners, laser welding in selected areas, and precision assembly between large modules. Those steps still need automation because accuracy and repeatability matter even more when fewer parts carry more structural responsibility. Final assembly also keeps its robots and automated tools. Battery installation, glass handling, seat movement, torque-controlled fastening, calibration, and quality control do not disappear because the rear structure came from a casting machine. So the better answer is not that Gigapress 4.0 deletes all robots. It deletes a large amount of traditional welding work. The factory still uses automation, but the machines are reassigned around a simpler vehicle architecture. And if Tesla is truly trying to shrink one department more dramatically than the body shop, The next place to look is not welding. It is paint. Paint is one of the most expensive rooms in a car factory, and it is easy to underestimate why. A normal paint shop needs surface cleaning, pre-treatment, electrocoating, primer, color coat, clear coat, curing ovens, filtration, humidity control, and large ventilation systems to manage chemical exposure. That creates three problems at once. It takes time, it consumes major energy, and it produces emissions that automakers spend heavily to control. The paint itself can release volatile organic compounds, and the ovens add another energy penalty because every painted body has to move through heated curing stages. This is where the cybercab story becomes more interesting than the exaggerated welding headline. Tesla has described a reaction injection molding process for selected exterior panels, where color is built directly into the part instead of being sprayed on afterward. In simple terms, the panel is not made first and painted later. The material chemistry, the mold surface, and the pigment system work together so the finished exterior piece can come out with its final color already in it. That does not mean the entire vehicle suddenly needs no finishing work. Glass, structural parts, closures, trim, and other surfaces still have their own manufacturing requirements. But for the panels that use this process, Tesla is targeting a much shorter color processing step, lower emissions for those parts, and the removal of paint shop volatile organic compounds from that specific operation. The manufacturing payoff is not just environmental. If color can be created inside the molded part, the factory can avoid some of the bottlenecks that make paint shops so slow and capital intensive. Fewer spray stages, fewer curing constraints, and fewer chemical control systems can change the economics of the vehicle. That is the twist. The loud story was about a mythical Gigapress that deleted every welding robot. The quieter, real breakthrough may be a color-in-panel process that attacks one of the oldest and most expensive parts of car production, paint. The important signal is that Tesla is no longer alone in chasing this direction. Across the industry, automakers are studying large aluminum castings because the basic attraction is obvious. Replace many stamped and welded parts with one or two major structural pieces, then build the car with fewer joints, fewer fixtures, and fewer assembly steps. That is why the trend now reaches beyond Tesla. Volvo-related manufacturing plans have been linked to orders for 9,000-ton class casting presses, and other companies, including Hyundai, General Motors, Xpeng, Giga, and several Chinese electric vehicle makers, have explored similar approaches. The details vary by platform, factory and supplier, but the direction is consistent. Simplify the vehicle body by making bigger structural sections in fewer operations. For a competitor, the calculation is not just about copying Tesla. A large casting can reduce part count, shorten the body shop, cut robot stations, and make a new electric vehicle platform easier to assemble at scale. In a market where margins are tight and battery costs still matter, removing complexity from the structure is a serious advantage. The trade-off is that big castings move risk into a different place. If one huge casting has a defect, the scrap cost can be high. If the casting process is unstable, production can suffer quickly. And after the car reaches customers, repairability becomes a real concern, because a damaged large structural section may be harder and more expensive to fix than a conventional assembly made from smaller replaceable parts. That is why insurance companies, collision repair networks, and manufacturers are watching this carefully. Giga casting can make production cleaner and faster, but it can also change the economics of accidents. So the real story is not that every automaker believes in a fictional 50,000-ton monster press. The real story is that Tesla pushed the industry toward a manufacturing race, and competitors are now deciding how much of that risk they are willing to absorb. So the verdict is clear. There is no confirmed 50,000-ton Gigapress, and no proven mass deletion of half the factory robots. Tesla's real breakthrough is more grounded and more important. Gigacasting, unboxed assembly, Fremont's Optimus conversion, and color in-panel production all point toward fewer steps and faster builds. Thanks for watching. If a viral manufacturing claim sounds too clean, question it. Write a comment with the next Tesla production bottleneck you think matters most.